Learn like a pro.
Today, we're going to go on a pretty wild chemical journey. We're going to see how you can take a totally stable substance and basically smash it back into its fundamental parts. And trust me, some of those parts can be, well, pretty dramatic. So let's just kick things off with a big question, right? How in the world do you take something as boring as table salt and reverse engineer it back into a super reactive explosive metal and a pale green poisonous gas? I know, it sounds like something straight out of a movie, but the chemistry is actually surprisingly simple.
And the answer is this thing, an electrolytic cell. The easiest way to think about it is like a battery, but in reverse. You know how a battery uses a chemical reaction to create electricity? Well, here we're using electricity to force a chemical reaction to happen, one that would never ever happen on its own. This cell is basically the engine for our whole trip.
All right, so our journey is about to begin, but before we hit the road, we need to meet our travelers. And in this story, the travelers are the ions.
Now we're specifically talking about what chemists call binary ionic compounds. Don't let the name scare you, it's a really simple idea. Binary just means two, so it's a compound made of only two different elements that have bonded together. That's it. And here are a few perfect examples. You've got sodium chloride, our good old table salt, which is made of a positive sodium ion and a negative chloride ion. But you see the same exact pattern with something like lead fluoride or even aluminum oxide. In every single one of these, you have just one type of positive ion, which we call the cation, and one type of negative ion, the anion.
Okay, so every journey needs a destination, right? Inside our electrolytic cell, that power supply we talked about creates two oppositely charged terminals. These are the destinations for our ions. We call them the cathode and the anode.
And you know what? The entire migration, the whole reason this process even works, comes down to one of the most basic rules in all of science. Opposites attract. That is the one and only rule our ions need to follow.
So it becomes this perfectly organized trip. The cations, which are the positive ions, are naturally drawn to the cathode, which is negative. And at the exact same time, the anions, our negative ions, head straight for the anode, which is positive. See? No getting lost, no confusion, they know exactly where they're going.
Let's follow what happens with our molten sodium chloride. First up, the negative chloride ions arrive at their destination, the positive anode. Now, because they're negative, it means they're carrying extra electrons. To become neutral again, they've got to ditch those electrons. This process of losing electrons is called oxidation. And a great way to remember that is with the phrase oil rig. Oxidation is loss.
Now here's the cool part. While that's happening at the anode, the positive sodium ions are finishing their journey over at the negative cathode. Because they're positive, they're actually missing electrons. So they arrive and pick up the electrons they need to become neutral sodium atoms. This process is called reduction. And thinking back to our mnemonic, oil rig, reduction is gain. It's that simple. And this isn't just some neat lab trick, by the way. This is how we produce tons and tons of essential metals, like aluminum.
So, what about the roads themselves, the actual physical terminals? Well, these electrodes are super important. They have to act as the platform for these reactions, but they absolutely cannot get involved themselves. They need to be what we call inert. The two most common choices for these inert electrodes are graphite and platinum. Think of graphite as the budget-friendly option. It's way cheaper and can handle crazy high temperatures. But there's a catch. If your reaction produces oxygen, the hot graphite will actually react with it and literally burn away over time. Platinum, on the other hand, is the premium choice. It's incredibly unreactive. The downside? It's ridiculously expensive. So you've always got this trade-off between cost and performance. Now, what's really cool about all of this is that the journey we just watched with sodium chloride, it's not unique. It follows a super predictable pattern, and once you learn the rules of the road, you can predict exactly what's going to happen with all sorts of different compounds.
And this table shows that pattern perfectly. Just look down the columns. Take potassium iodide. At the anode, you get this beautiful violet iodine gas. At the cathode, you get potassium metal. Same deal for copper chloride. You get green chlorine gas and copper metal. It's always the same story. The negative ion makes a nonmetal at the positive anode, and the positive ion makes a metal at the negative cathode, every single time.
All right, you've seen the whole journey, from the travelers to the destinations to the predictable outcomes. You think you've got it down? Let's do a quick knowledge check and find out.
Question 1. During electrolysis, where do those negative ions, the anions, travel to? Just think back to that one fundamental rule. Opposites attract.
Question 2. What's the colorful gas that forms over at the anode when you run electrolysis on molten copper chloride?
Number 3. Which electrode is the cheaper one but has that big disadvantage of burning away if you're not careful with the temperature and oxygen?
Okay, question 4 is a fill in the blank. To go from being a positive ion back to a neutral metal atom, a cation has to gain electrons or lose electrons. And for the final question, if you perform electrolysis on molten lead oxide, what are the 2 products you're going to end up with?
So there you have it. We've totally nailed how this works for molten compounds, where it's just our 2 ions on the road. But that brings up a really interesting final question, doesn't it? What happens if you try to do this in water? Does the water just sit back and watch, or does it decide to join the Great Ionic Migration itself? Now that's a story for another time.